The next speaker is Thiem Hoang from CETA. He will talk about the anomalous microwave emission from maybe spinning clock.
Hello? Hello. Hi, everyone. So today I'm going to talk about our new results on anomalous microwave emission. And if these results will be confirmed, we will welcome a new dust population in the interstellar medium. So let's talk about what are those dust populations. So here are my collaborators, including Alex Lazarian, Crutcher, and Peter Martin, and my PhD student and my collaborator from Vietnam. So our ISM are as the CMB foregrounds for cosmic microwave background studies. So traditionally, our ISM produce three components of foregrounds, including thermal dust emission, synchrotron emission, and free field emission. If you look at this plot, you see that there is a range of frequency in which foreground emission is very minimal. So this is a range that cosmologists really like to design the experiments because they think that the CMB foreground is very small. However, in 1996, the Kobe team, led by Al Kogat, they discovered that in addition to three known foreground components, we have an emission excess at this frequency, 31 gigahertz. And they didn't know what is the origin of this emission excess, so they came up with the name anomalous microwave emission. 1 year later, Lesh et al. Also found the emission excess at two frequencies. Right after that, Thiem and Lazarian, they came up with two models to explain the origin of anomalous microwave emission. The first model is electric dipole emission from rapidly spinning ultra-small dust grains. So this mechanism is emission by rotating nanoparticles. At that time, the simple assumption is that nanoparticles are polycyclic aromatic hydrocarbons because there were observations in mid-infrared emission that show the signature consistent with the pH emission. They also proposed another emission mechanism, namely magnetic dipole emission from fluctuation of magnetization within magnetic nanoparticles. So, right after the model by Thiem and Lazarian, a lot of observations made in particular by Angela Rodeo Veracosta and Doug Finkbeiner. So they did very numerous observations, and all observations support the idea of spinning dust emission. And recently, there are many more observations in different environments. Okay, so this is a beautiful plot by Planck Collaboration. So where they show the observation by Planck, the thermal dust emission, the free emission, and the spinning dust emission here. So you can see that this bumpy feature is excellently fitted with spinning dust emission. So this spinning dust emission is real. The question is, what is the exact carrier of this emission component? Is the carrier polycyclic aromatic hydrocarbons or something else? And Thiem and collaborators made a very important attempt to search for the confirmation of pH. So the idea is that they use the observation from WISE satellite and the AME, anomalous microwave emission from Planck. Because they expected to have a correlation between anomalous emission and pH abundance if anomalous emission is from spinning pH. Well, as you can see from here, there are no any correlation between pH abundance here and anomalous emission. So what is wrong with it? Are there any alternatives to spinning pH or not? Let's look at the physical mechanism of spinning dust emission. So the mechanism is very elegant. We have some dipole moment, and we need to have ultra-fast spinning. Okay? And This is the original model by Trainer Lazara in 1998. So they assume that our smallest grain is pH and it's spinning around symmetry axis. And this is the modern model developed by us. It consists of spinning around symmetry axis and the precession of symmetries around the angular momentum. And we take into account the thermal fluctuation within nanoparticles. Okay, so the first idea is that anything that has dipole moment and anything that spinning extremely fast can produce anomalous emission. So now, how about silicon nanoparticles? It's like our very small sand nanoparticle here. And for each silicon oxygen molecule, it has a dipole moment about 3 dipole dBi. Silicon carbide has a dipole moment about 5.6, and so on. So even if each nanosilicate particle has one silicon oxide attachment to the ash, it can produce some considerable dipole moment. And nanoparticles are always spinning extremely fast because of small size and because they interact or they collide with the atoms and UV photons in the interstellar medium. And then they should produce rotational emission. And here I show the results we calculated for different dipole moment per atom in nanoparticles. Beta is 2.2 dBi to 1 dBi. And for each value of dipole moment, we change the abundance of nanoparticles from 1 to 20%. So if we increase the abundance of nanoparticles, we increase the emissivity by spinning nanoparticles here. And if we increase the dipole moment, we have the reduction in the, we have an increase in the spin dust emissivity. And we show the data collected by Finkbeiner in 2004. So as you can see that spinning nanosilicates emission can reproduce very well the anomalous microemission observed. Okay. So now, we also realize that nano iron particles also have a magnetic dipole moment because nano iron particle has a spontaneous magnetization. They are ferromagnetic materials. And nanoparticles are always spinning, so they can produce spinning emission. But because iron nanoparticles have a much smaller dipole moment than nanosilicate, and also they have a small abundance. So if we assume that all iron nanoparticles are in, all iron abundance is in nanoparticles, we can see that the emission by spinning iron nanoparticles alone cannot reproduce the observed anomalous emission, but they still contribute some level, right? Okay, so how about magnetic dipole emission? And we realize that the original idea of magnetic dipole emission found that if magnetic dipole emission is produced by free-flying nanoparticles, then the original estimate found that the polarization level is very high, and many people take the estimate as very seriously, and they compared the observation, and they found that the estimate of polarization by spinning iron nanoparticle is very large, and it cannot be consistent with observation of anomalous microemission. But our recent result, we show that the polarization by iron nanoparticle anomalous emission by iron nanoparticle is also within the observation limit. I will show you later. So now, how to distinguish different carriers of anomalous emission? We have a spinning pH, we have spinning silicate, we have a spinning iron nanoparticles, and we also have a magnetic dipole emission. If we look at the emissivity, we cannot distinguish them because they are producing only the same comparable amplitudes. And we realize that if we look at polarization, we can distinguish different carriers. Okay, so here is the polarization we predicted for spinning emission from nanosilicates, and we calculated the polarization as a function frequency for beta from 0.1 to 0.8 dBi. So if we increase the dipole moment, we have a stronger rotational damping, and the polarization decrease. And this symbol shows observational data by different experiments by Quixote and also by Planck. And you can see that for some value of dipole moments, the polarization is consistent with observational data. Okay, so the polarization of spinning iron nanoparticles. So iron nanoparticles have a much larger magnetic susceptibility than spinning silicates. So as a result, they produce larger polarization. And now, if we put them together, the polarization by spinning dust and the polarization by magnetic dust here. And here are observation data. So you can see that the polarization from spinning dust and magnetic dust are well within the level of observational data. Interestingly, you can see that this feature in observational data can be reproduced with the polarization from magnetic dipole emission here. You might criticizing that this level of observational data are much above the level of predicted polarization. Fortunately, the latest result by Quixote show that the polarization at this frequency are much lower, so it would be here. And so it's become more consistent with our prediction. Okay, so let me summary. So the idea of anomalous microemission is real, but the exact area is still unknown. And we show that we might have a new dust population in the interstellar medium, namely silicate nanoparticles or iron nanoparticles. This new dust population can produce considerable anomalous microemission, and the polarization level is consistent with observational data. And if my prediction here are confirmed, we will welcome new dust population, namely nanosilicate and nanoiron particles in the interstellar medium. Okay, so another thing, if we have an iron nanoparticle in the interstellar medium, there may be more likely iron nanoparticles embedded in big silicate grains, right? And if that happens, the big silicate grains have an enhanced magnetic susceptibility, and it results in the new or unified model of grain alignment that we propose in this paper. So the conclusion is that we may have not only the ugly guys in the interstellar medium or like a pH, and we may have more friendly nanosilicate particles in the interstellar medium, or we may have both. And what happens if we have both? Okay, it can explain the two spinning dust components, one at low frequency here and one at large frequency here, that is observed by Planck satellite. So I want to thank you very much for your attention.
What is the infrared emission you expect from those nanoparticles? Aren't they going to show up in the near infrared, mid infrared?
So it depends on the abundance of those nanoparticles. Yeah, they should, of course, exhibit in mid infrared emission, but with the abundance less than 10% of total abundance, it is within the level of mid-infrared emission that was evaluated by Drain and Lee in 2002. We also checked the possibility of if nanoparticles can result in the polarization in the UV, because nanoparticles may have a partial alignment. But within like a 10% of abundance, and also some range of dipole moment, they cannot exceed the level of UV polarization observed. So one of the implications of this study is that it may provide some new constraint on the dipole moment and abundance of nanoparticles if we combine multiple choices.
Thank you.
Only one question, Chair.
Thiem, I think the answer to this is probably on one of your plots, but if in a typical SMA, karma, ALMA, 1000 AU dense core observation of a few % polarization from dust, what fraction of that might be coming from these new magnetized nanoparticles? Is it going to dominate, or are we still going to be looking at the micron-sized dust particles?
So you're saying that the progression from dense core, right? Okay, so for dense core, we may have a depletion of nanoparticles because of the dust growth.
Even at 1,000 AU scales?
Yeah, I think so.
So you're talking very diffuse.
Yeah, we're talking
emission in your
about
talk.
diffuse medium.
Okay.
But if we go to very dense core, the dust coagulation happens.
All right.
And the observation by Chris Tibbs, so they found that there are a very small level of nanoparticles by using camera data, actually. Yeah.
Thanks.
Okay, thanks, Tan. Our